Hi, my name is Jake, and I'm here to talk about LiDAR scanning pipes. For ENME435, our goal was to understand the fundamentals of remote sensing by building a functional LiDAR scanner that can 3D scan an object. The object I picked in this case was these pipes outside of A. James Clark Hall right behind. I picked them because they seemed big and somewhat interesting enough with a slightly different shape. Nothing super complex, but nothing super simple either, which is a great test of the capabilities of a LiDAR scanner. As for how a LiDAR scanner works, we first have to look at these two equations. First is the range equation, which basically says how long it takes, which determines the range of a scan by use of the speed of light times the distance traveled over 2. And then we have the LiDAR equation below it, which is about the number of photons received as a function of the number of photons transmitted. And you can see the interaction between radiation and objects up here as well. Now, my scanner was a geometric scanner, which means that this distance between the laser and the camera allows us to determine a distance between the scan and the object. Basically, if the thing that we are scanning is further away, it'll appear closer towards the center relative to what the camera is scanning. And if it's closer, it'll be closer towards the edge relatively. And through trigonometry, we can get this formula, which has the pixels, which is a pixel count from the center as this PFC value, and then RPC and RO are correction values in order to make sure that we get the right image. This is my LiDAR scanner. It's a 3D printed shell with a mount for a tripod. It has an Arduino that isn't really doing a lot, a laser that is powered by a battery pack, or the Arduino if you'd like, and a Raspberry Pi for the camera and sensing. There's also a battery pack that powers the Raspberry Pi, and I use my phone as a way to get angles, and all mounted on a tripod. To set up the scanner, we first took many different scans of the same place, but at different distances away, so about 6 inches every single time. And you can see here that I have 2 images, for example. We then can figure out the distance to the target and the pixels from the center in order to get a correct PFC value for when we want to scan things. And after that, you calibrate everything and you get a curve that looks something like this with the correct RPO and RO and RPC values. So here I am at the final target location, and I just completed my full 360 scan of the target. So how I had it is that we have the scanner over here, and it's about 7 feet away from the pipes. I did this in multiple locations. You can see these little bits of painter's tape on the floor that mark some of the locations I filmed at. And while I already did data acquisition, we simply scan similar to how we were doing on the one part, and we're just doing that multiple times over. Once we run through all the proper scanning functionality, we get a bunch of pictures that look something like this. And we run these pictures through a code that masks the image and grabs just the laser light, and then graphs that in 3D space. And thus, we can move on to graphing this in MATLAB to show this 3D space itself. Difficult. However, I've gone through and graphed the point cloud of most of the points that I could use. We have a few figures, one that combines all of them, and one individually for each of the different ones. The way I tried to orient them together is by use of the rigid T-form 3D function, which basically we can assign rotation angles and translation coordinates to a point cloud and thus orient them. This is a lot harder to get right in 3D space, especially when you kind of have to eyeball it. So I already run the code. So here are a bunch of the graphs for the different ones. I did about 8. And these 3 over here, the reason the graphs are so small is because they detected like small amounts of points really far away, which are most likely due to ambient lighting or resultant leftover parts from the HSV Max that I wasn't able to erase without making the quality of the laser much lower than I wanted it to. Not that bad in retrospect, because again, the coordinates of all of them are pretty similar, even with this like random offset values. So it would be manageable. But as you can see, we got a bunch of different views. We have ones from like the back. We have ones from the side. We have ones from the front. We have a bunch of different views. And as mentioned before, there is a graph over here where this is a very chimera resultant, as in I didn't try and orient all of them together. I was trying to orient like 2 or 3 of them together, and it proved a much more strenuous task than I had the time for. I will try and fix this before my final video, but I thought I would just go with what I have so far. Some interesting notes are that because of the way that my image is oriented, which are 2 pipes near the A. James Clark building and the Kim Engineering building, there were a lot of times where the laser scan actually did get these lips of the pipes, even when it was like from the back or from like a slight angle at the back. So you can see that many of the scans, even though this one was like almost from the back directly, or like this one was from the front, you can still get, even though we're missing like so much of this from the first pipe, we are getting that dimensionality through the scan. So it picked that up quite well. I think the scan was overall very good, and the only hampering was, of course, my ability to code this in a way that they can properly be shown all together and create a proper 3D mesh. Here we ended up with a mesh that doesn't really look very representative based on exactly one scan, and could have looked a lot better when using the other scans in tandem with each other.